Hello everyone, this is Siddiq Rahman and welcome to the third lecture of the fifth week. So let's start. By the end of this lecture, you guys will able to describe about parity. From this slide, we may learn, or you guys will learn, what this lecture will cover. You guys will learn such as parity bit, the overview of parity generator, working function of parity generator, and its classification. Not only this, you guys will learn even parity generator and odd parity generator also. So let's start with the general overview. The parity generator and parity checkers main function is to detect errors in data transmission, and this concept is introduced in 1922 in RAID technology. The parity bit and the parity checker are used to guard against data loss. The parity bit is an extra bit that is set at transmission side to either 0 or 1. It is used to detect only single bit error, and it is easiest method for detecting errors. There are different types of error detection codes used to detect the errors. They are or such as parity, ring counter, block parity code, Hamming code, and biquinary, etc. From this slide, we may learn about parity bit. So let's start. The parity bit or check bit are the bits added to the binary code to check whether the particular code is in parity or not. For example, whether the code is in even parity or odd parity is checked by this check bit or parity bit. The parity is nothing but number of ones, and there are two types of parity bits such as even bit and odd bit. In odd parity bit, the code must be in an odd number of ones. For example, we are taking 6-bit code such as 100011. This code is said to be odd parity because there is 3 number of ones in the code which have been taken. Well, on the other hand, in even parity bit, the code must be in even number of ones. For example, we are taking 6-bit code such as, or as for example, 101101. This code is said to be even parity because there are 4 number of ones in the code which we have taken. Now from this slide we may learn what is parity generator. So let's start. The parity generator is a combination circuit at the transmitter. It takes an original message as input and generates the parity bit for that message, and the transmitter in this generator transmits messages along with its parity bit. Now from this slide we may learn the working function of parity, or you can say parity generator. So let's start. Assume that assume that your final message is an n-bit stream of digital data. One of the bits is the parity bit. Well, to transmit this bit stream containing n-1 data, which is message signal, plus one additional parity bit, we require a special circuit known as parity bit generator. Well, the parity generator is a combinational logic circuit. The parity generators can create two parities. One is even parity, which generates a final message with an even number of ones. So the parity bit for an even number of ones is 0. On the other hand, another number is an odd parity, which generates when the total number of ones in the bit stream is odd. From this slide, we may learn the classification of parity generator. Parity generator is classified into two types. One is even parity generator and another one is odd parity generator. From this slide, we may learn the overview of even parity generator. So let's start. The even parity generator maintains the binary data in every number of ones. For example, the data or the data taken is in odd number of ones. This even parity generator is going to maintain the data as even number of ones by adding the extra one to the odd number of ones. This is also a combinational circuit whose output is dependent upon the given input data. So this is an important sentence to be remembered. So don't forget this sentence, which means which means the input data is a binary data or binary code given the parity generator. Now, from this slide, we may learn the truth table of parity generator. So let's start. Let us consider three input binary that 3 bits are considered as or symbolized as A, B and C. We can write 2 to the power 3 combination using the 3 input binary data, that is from 0, 0, 0 to 1, 1, 1, which means 0 to 7. Total 8 combinations we'll get from the given 3 input binary data, which we have considered. The truth table of even parity generator for 3 input binary data is shown in below. Well, we have already mentioned in the paragraph that we get 8 combination. For the space issue, we are representing in this slide only 2 combination, and in the next slide we are representing the rest of the combination. So let's start. When the input is 0, 0 and 0, what does it mean? Okay, so the description says about this combination: in this input binary code, the input parity is taken as 0 because the input is already in even parity. So no need to add even parity once again for this input. Next one or next combination, which is 0, 0, 1. In this input binary code, there is only a single number of 1, and that single number of 1 is an odd number of 1. If an odd number of 1 is there, then even parity generator must generate another one to make it as even parity. So even parity is taken as 1 to make 0, 0, 1 code into even parity. So let's move into the next slide. Next combination is 0, 1, 0, which means this bit is in odd parity. So even parity is taken as 1 to make the 0, 1, 0 code into even parity. Next combination, which is 0, 1, 1, this bit is already in even parity. So even parity is taken as 0 to make the 0, 1, 1 code in even parity. Next combination, 1, 0, 0. This bit is in odd parity, so even parity is taken as 1 to make the 1, 0, 0 code into even parity. Next combination is 1, 0, 1, which represents this bit is already in even parity. So even parity is taken as 0 to make the 1, 0, 1 code into even parity. Next combination, which is 1, 1, 0. This bit is also in even parity. So even parity is taken as 0 to make the 1, 1, 0 code into even parity. Next one, and the last one is next one, which is also last one, and which is 1, 1, 1. This bit is in odd parity, so even parity is taken as 1 to make the 111 code into even parity. Now if we complete our truth table, then we get this table, and if we just pick a number or pick a random input value, such as when the value of three inputs are 1 0 0, in that case the even parity is 1, and when the value of inputs are 1 1 1, in that case the even parity is also 1. But when the input values of when the value of inputs are 0 1 1, in that case the even parity will be 0. Now if we convert the founded truth table into K-map simplification or into K-map, then we get the upper rightmost figure. Okay, and in this slide you may notice that I have attached also the previous truth table for your understanding how we convert from the truth table to K-map. And the K-map simplification for 3-bit input even parity is as follows. And if you look at the bottom right figure, then you may find another K-map is represented here, and also just in this in 4 cells there are also just a number which is 1. And if you see in the truth table, I have also marked in red marks which have one even parity. So we just indicated in the bottom right K-map just 1 for writing our Boolean function in the next slide, which will help you to understand how can we write the Boolean function from the truth table as well as from the K-map. Okay. Well, from the even parity, now from this slide, sorry I repeat again, from this slide we may learn how to write the Boolean expression for even parity generator. So let's start from the even parity truth table. The parity bit simplified expression is written as follows. So in this slide we may again see our previous truth table, and with addition to just some of the alphabets, some of the extra alphabets. If we see the first even parity is 1 when the value of inputs is 0 0 1, and if we write the Boolean expression for this condition, sorry I repeat again, for this 1, so we may write the value of 0 we cannot use for A, that's why we write not A, and same as for the value of B, because the value of B is also 0, that's why we can write not B, and the value of C is 1, that's why we do not use any not for the C, that's why we write A bar, B bar and C. And those who have, or those for the rest of the ones we can write in this way, so I hope there is no problem for this issue. And if we write, if you guys see in the right section of this expression, then you will find the P even means even parity. P even represents the even parity, and which has equation A, B bar, C bar. Sorry I repeat again, inside of the first parenthesis, A and not B and not C, or not A and not B and C. After the first parenthesis, or again second parenthesis started, and inside the second parenthesis we can find A and B and C, or not A, and B and not C. And if we simplify this expression, then we may find B not XOR A XOR C. And I hope you guys I hope you guys are understand that how to simplify this expression, as you guys have already known that how to simplify the given Boolean expression. So there is no confusion and there is no problem for this expression. So let's move into the next slide. From this slide, we may learn the logic circuit of event parity generator. So let's start. The event parity expression implemented by using two XOR gates. And the logic diagram of the event parity using the XOR logic gate is shown below. And if you guys remember the Boolean expression from the previous slide, then you may find B XOR A XOR C, or you can say A XOR B or A XOR B XOR C. That's why we need two XOR gate, and in the output section we can get the event parity which is either 0 or 1 for the defined condition. And that's all for event parity generator. So let's move into the next slide. Now time to learn, or time has come to learn about another classification of parity generator, which is odd parity generator. So let's start. The odd parity generator maintains the binary data in an odd number of ones. For example, the data taken is in even number of ones. This odd parity generator is going to maintain the data as an odd number of ones by adding the extra one of, sorry I repeat again, the extra one to the even number of ones. This is the combination, sorry I repeat again, this is the combinational circuit whose output is always dependent upon the given input data. If there is an even number of ones, then one parity bit is added to make the binary code into an odd number of ones. Now, from this slide, we may learn the truth table and as well as the description of the values of inputs representation. So let's start. Let us consider three input binary data that 3 bits are considered as A, B, and C. The truth table of odd parity generator of 3 input binary data is shown below. Well, when the values of inputs are 0, 0, 0, what does it mean? It means in this input binary code, the odd parity is taken as 1 because the input is in even parity. Next combination, 0, 0, 1. This binary input is already in odd parity, so odd parity is taken as 0. 0, 1, 0. This binary input is also in odd parity, so odd parity is taken as 0. Next combination, 0, 1, 1, which means this bit is in even parity, so odd parity is taken as 1 to make the 0, 1, 1 code into odd parity. The rest of the combination of the inputs are given in this slide, or you can say the represented in this slide. So let's start. The combination of 1, 0, 0, which means this bit is already in odd parity, so odd parity is taken as 0 to make the 1, 0, 0 code into odd parity. Next combination, 1, 0, 0. Sorry, I repeat again, 1, 0, 1. This input bit is in even parity, so odd parity is taken as 1 to make the 1, 0, 1 code into odd parity. Next combination, 1, 1, 0. This bit is in even parity, so odd parity is taken as 1. Last one, which is 1, 1 1, and which means this input bit is in odd parity, so odd parity is taken as 0. And finally the truth table looks like this. If we take the values of from the truth table, the values from here, just random values, pick just 1 or 2. 1, if we select 1 0 0, then we get in the output section, or the output parity is 0, or you can say the column of odd parity represent 0. If we choose 1 1 0, in that case we get 1. From this slide we may learn the Karnaugh map about odd parity generator. So let's start. The Karnaugh map, or you can say K-map simplification for 3-bit input odd parity is as follows. So this slide has two sections. One is left section and another is right section. The truth table has already discussed in the previous slide, and in here just attached this truth table because to understand how to convert this truth table into K-map. And if you see the upper right figure, then you may find the exact truth table conversion, and which is also represented in right upper corner of this slide. And in the bottom right figure you may find whatever we find in the odd parity, and also 1 which is indicated in the right bottom figure, and we don't count any 0 for our Boolean function. So that's why a question may arise, why we count only 1. We are writing the Boolean expression of this parity generator by using only 1. So let's move into the next slide. From this slide we may learn the Boolean expression of odd parity generator. So let's start. From the odd parity truth table, the parity bit simplified expression is written as in the right section of this slide, and in the left section of this slide, if we see, then we may find when the values of inputs are 0 0 and 0, in that case we get 1 in the odd parity column. And if we write for the Boolean expression of this row, then we get a not a, or you can say a bar, not b or b bar, and not c or c bar. That's why in this way the rest of the ones should be written as follows. And if we see in the right section of this slide, then we find the Boolean function of odd parity generator, which is represented as or symbolized as p odd is equals to, inside of the first parenthesis we get not a and not b and not c, or a not b, a and not b and c. First parenthesis is completed, after that or and second parenthesis is has been started, and we get not a and b and c, or a and b and not c. And if we simplify this expression, then we can find the last line, or you can say the second line of the expression. So let's move into the next slide. From this slide we may learn the logic circuit of odd parity generator. So let's start. The odd parity expression implemented by using one XOR gate and one XNOR gate, and the logic diagram of the odd parity generator, or you can say odd parity using the XOR logic gate is XOR as well as XNOR is shown in below. And if you see, then you may find from the figure input A and input C, which is connected by a XOR gate, and whatever we get the output from this gate, which is also used as an input of XNOR gate, and another input of XNOR gate should be uh, input B, and in the right side you may find the output of odd parity generator. So let's move into the next slide. In the next lecture you guys will learn about parity checker. That's all for this lecture. Thank you guys for your attention. See you guys in the next lecture. Till then, thank you.